Today we're going to talk about elemental composition of pure substances. Now first, let's do a little review. So, what is a pure substance? A pure substance is a substance that has a constant composition. That means it's not a mixture of different things. Pure substances are either elements or compounds, and this includes both covalent and ionic compounds. Another thing we need to review is the law of definite proportions. Basically, the law of definite proportions states that a given chemical compound is always going to have fixed and constant proportions of its elements by mass. For example, a sample of pure water is going to contain 11.19% hydrogen by mass and 88.81% oxygen by mass. Now, it doesn't matter how much you have, doesn't matter if you have a lot of water or a little water, as long as it's pure, it doesn't matter where the water's from. It's always going to have this same ratio of hydrogen to oxygen by mass. And this holds for both covalent compounds and ionic compounds. Now, the next thing we need to talk about is mass percent composition. Now, this goes by a whole bunch of different names. You'll sometimes hear the word mass percent, but the mass percent composition of a particular component in a compound, such as a hydrogen in a water molecule, is the mass of an element in that particular compound divided by the mass of 1 mole of the compound times 100%. Now, when we're doing mass percent composition and we're trying to figure out the mass of any particular element in a compound, we look at each element in the compound separately. We'll do an example in a moment, but here's an overview. The first thing you do is find the molar mass of the element by looking at the periodic table. Then you find the molar mass of the compound, and you do this by looking up all the atomic masses of the atoms in it, and you add all those molar masses up. Make sure you account for the number of copies of each atom in the compound. For example, in water we have 2 hydrogens. Don't leave one of those hydrogens out. Once you have the molar mass of the element and the molar mass of the compound, you're going to divide the molar mass of the element by the molar mass of the compound. Now, let's look at an example. Here we have ethanol, C2H6O, and we want to find the mass percent composition of carbon, hydrogen, and oxygen in this molecule. First thing we're going to do is go to the periodic table, and we're going to look up the molar masses of carbon, hydrogen, and oxygen. Second thing we're going to do is calculate the molar mass of ethanol, and we do this by adding up the masses of 2 carbons, 6 hydrogens, and 1 oxygen, and we're going to get 48.068 grams per mole. Third thing we do is we're going to calculate the mass percent for each element, and we're going to do this by taking the molar mass of the atom or element and putting that in the numerator, and then taking the molar mass of the molecule and putting that in the denominator. And then we crunch these numbers out, and we find that we have 52.14% carbon by mass, 13.13% hydrogen by mass, and 34.73% oxygen by mass. And since these are the only 3 elements in this molecule, if we add them all up, we should get 100%. And we do. So that is how we do percent composition by mass. Now let's talk about determining the empirical formula of a compound. An empirical formula gives you the relative proportions of the elements in a compound. It is written in terms of the smallest whole number ratios of the atoms in that compound. It's important to remember that an empirical formula doesn't give you the actual numbers or arrangement of the atoms, only the relative proportions of the atoms in the formula. The empirical formula is different from the molecular formula, which is the fancy name for the actual formula. The molecular formula is going to be some multiple of the empirical formula. For example, let's say you have glucose, C6H12O6. The empirical formula for this is going to be CH2O. The lowest whole number ratio of C to H to O is 1 to 2 to 1. Now when we look at the molecular formula, you'll notice that 6 to 12 to 6, those are the subscripts on C6H12O6. Well, those simplify to 1 to 2 to 1 if you divided them all by 6. This table shows you some examples of molecular formulas and empirical formulas. In order to get the empirical formula, you divide the subscripts on all of the different elements in the molecular formula by the greatest common factor. So for water, the molecular and empirical formula are the same. But for ethylene, we divided each of the subscripts by 2 to get the empirical formula. If we take a look at glucose, you notice that we divided all the subscripts by 6 to get the empirical formula. For hydrogen peroxide, we divided by 2, and for hydrazine, we also divided by 2. The ratio of elements is the same in the empirical formula as in the molecular formula. The empirical formula has just been simplified in a way. Empirical formulas are typically found through experimental data. One of the ways you can do it is to take your substance and break it down through a decomposition reaction where you break it down into all of the elements that make it up. For molecules that contain carbon and hydrogen, they'll often do a combustion analysis where they burn a small amount of a compound and then measure the amount of carbon dioxide and water produced and use some stoichiometry to figure things out. And this is a little bit more complicated. We're going to be focusing on the decomposition reactions. In empirical formula problems, you may be given the masses of 2 or more elements after the decomposition of a compound, or the amount of carbon dioxide and water produced if this is a combustion reaction. Let's talk about how to calculate the empirical formula for a decomposition reaction. If they give you mass data, the first thing you're going to do is use this to determine the number of moles for each element, and you do this by using the molar mass. Once you've done this for all the elements in the compound, the next thing you're going to do is figure out which one has the smallest molar amount. In other words, which one is there the fewest moles of? And for each of the elements, you are going to take the moles that you calculated and you're going to divide them by the smallest number of moles. This will give you tentative subscripts. If these subscripts are whole numbers, you're good and you can stop there. But often you're going to get something that's a decimal. And what you're going to have to do is multiply all those subscripts by the same integer so that you get whole number subscripts. This nice little diagram also shows the steps, and this is in your notes. Let's look at an example. We're told that a sample of the black mineral hematite contains 34.97 grams of iron and 15.03 grams of oxygen. We want to know what the empirical formula of hematite is. So we have been given the masses, and what we need to do is go to the periodic table and find the molar mass. So 1 mole of iron has a mass of 55.85 grams. 1 mole of oxygen has a mass of 16.00 grams. We're going to use the molar mass to find the number of moles we have of each element. And we do this using dimensional analysis. Multiply your number of grams by your conversion factor, moles on the top, grams on the bottom. So we have 0.6261 moles of iron and 0.9394 moles of oxygen, and we notice that we have fewer moles of iron. This is going to be our denominator for step 2. Now we're going to divide by the smallest number of moles, which is going to be 0.6261, and this is going to give us tentative subscripts. And we do that, and we get a subscript of 1 for iron and of 1.5 for oxygen. In this example, we're going to have to multiply this by something to get rid of that 0.5. And I take a look at this and I notice that if I multiplied everything by 2, then that 1.5 would turn into a subscript of 3. So I'm going to multiply my whole preliminary formula by 2. That gives me Fe2O3. So this is my empirical formula. And this example was, of course, an example of finding the empirical formula of an ionic compound. The same strategies used with a covalent compound as well. Now we're going to do a variation on this. Sometimes you're not going to be given mass. Sometimes you're going to be given mass percent composition data. In other words, you're going to get your data as percents instead of grams. And in order to solve these kinds of problems, we want to take advantage of the law of definite proportions. Just remember, it doesn't matter how much stuff we have, the ratio of elements is always going to be the same, regardless of whether we have a little bit or whether we have a lot. So if we're given our data in terms of percent composition, a trick that we can use is to pretend that we have 100 grams of our compound. We could have chosen any random number, but we choose 100 because it makes it a lot easier. And what we're going to do is we're going to multiply 100 by the mass percent composition data to get the mass of each element that we would have if we had 100 grams of the compound. And here is a nice little flow chart from OpenStax that shows you how to do this. We'll do an example. This example is for a covalent compound. We're told that the bacterial fermentation of grain to produce ethanol forms a gas with a percent composition by mass of 27.29% carbon and 72.71% oxygen. What is the empirical formula for the gas? Well, we're going to use our little trick. We're going to pretend that we have 100 grams of the element, and then we're going to proceed like we did in the previous example. We're given the fact that our compound has carbon and oxygen in it. We have translated our percentages into grams, so we're going to pretend we have 27.29 grams of carbon and 72.71 grams of oxygen. In order to find the empirical formula, first thing we're going to do is we're going to use our molar mass and dimensional analysis to find the number of moles we have of each element. Convert to moles, always the first step in an empirical formula problem. Once we do this, we see that we have 2.272 moles of carbon, 4.544 moles of oxygen. We have the smallest number of moles of carbon, so that's going to be in our denominator. Now for step 2, we're going to divide our number of moles by 2.272 to get our preliminary subscripts. And when we do that, we get a 1 for carbon and a 2 for oxygen. And our preliminary formula is CO2. Now, we don't have any decimal numbers on this, so we're done. We don't have to multiply by anything. CO2, our preliminary formula, is also our empirical formula. Just to reiterate, we can find empirical formula for ionic and covalent compounds. But one thing you should notice about the empirical formulas of ionic compounds, because of the way ionic compounds are defined, the formula for an ionic compound is always going to be the lowest whole number ratio of atoms. An ionic compound formula is an empirical formula. But for covalent compounds, that's not necessarily the case. And to find out what the molecule really looks like, we're going to have to find the molecular formula. Now, the molecular formula is the real formula, the one we see in chemical equations, how the molecule is put together. This shows the relative numbers of the elements that make up the compound, not just the proportions, the numbers. In order to find the molecular formula, we need to know the empirical formula, and we also need to know the molar mass of the compound or the molecular mass. Remember, there's a one-to-one translation between molar mass and molecular mass. We're just going from AMUs to grams. Molecular mass data is often found through mass spectrometry experiments and similar things like that. To find the molecular formula, we're going to compare the compound's molar mass to the empirical formula mass. To find the empirical formula mass, you find the molar masses of all of the atoms that make up the empirical formula, and you add them up. Once you have the empirical formula mass, you're going to calculate a number n. Using the formula, molar mass of the compound divided by empirical formula mass equals n. N is the number you're going to multiply all the subscripts in the empirical formula by to get the molecular formula. For example, say our empirical formula is AXBY and n equals 3. We're going to multiply both the subscripts x and y by 3. So our molecular formula will be A3x, B3y. Let's do an example. You have been given a compound with an empirical formula of CH2O. You calculate the mass of the empirical formula to be about 30 grams per mole. You did this by looking at the periodic table. Now you're told that the compound's molecular mass is 180 grams per mole. In order to get the molecular formula, all you have to do is use our equation. We are going to take 180 grams per mole, divide that by 30 grams per mole, and we are going to get n equals 6. We take our empirical formula and we are going to multiply all of the subscripts by 6, so that our molecular formula is C6H12O6, glucose. Let's summarize. A pure substance is a substance with constant composition that's not a mixture. Pure substances are either elements or compounds. The law of definite proportion says that a given chemical compound will always have fixed and constant proportions of its elements by mass. We can determine the mass percent composition of the elements in an ionic or covalent compound by using this formula. Mass percent composition equals the mass of an element in 1 mole of a compound divided by the mass of 1 mole of the compound times 100%. And you look at this separately for each element in the compound. Empirical formulas give you the relative proportions of the elements in a compound, and the formula for an ionic compound is actually an empirical formula. Molecular formula is the actual formula for a covalent compound, and it's going to be a multiple of the empirical formula. You can calculate the empirical formula by following the steps shown in this diagram. If you are given mass percent composition data, take advantage of the law of definite proportions and pretend you have a 100-gram sample of your substance. Convert to grams, find the number of moles, and use the same types of calculations you would use if you had been given grams. To find the molecular formula, calculate the empirical formula mass by adding up all the molar masses of the elements in your empirical formula. Then take the molar mass of the molecule, which you have been given, and divide that by the empirical formula mass to get n, which is the number you're going to multiply the empirical formula by to get the molecular formula.